Our next speaker is Professor Plamen Angelov. Professor Angelov is a fellow of IEEE and chair in intelligent systems at Lancaster University. He is director for Lancaster Intelligent Robotic and Autonomous Systems Center. He is governor of the International Neural Network Society, for which he also served as was president from 2017 to 2020. He has active research portfolio in the area for explainable deep learning and has international recognized resource into autonomous learning and evolving systems. He leads a number of projects funded by UK Research Councils, EC, European Space Agency, DSTL, GCHQ, and the industry. He has received several awards, including IEEE awards for outstanding contributions 2013 and 2017. He is editor-in-chief of Journal Evolving Systems and also associate editor for IEEE transactions on cybernetics, fuzzy systems, and on AI. Today, he will share his research experience on exemplar-based deep learning. Please join me in welcoming Professor Plamen Angelov.
You're muted, you're muted.
Hi, thank you very much for the kind introduction, Chair Gang. First of all, can you see my screen shared? Hello?
Yes, we can see your screen.
Okay. Okay, so thank you very much for this opportunity. It's really a pleasure for me because some 20 years ago or so, I started my research career in UK from Loughborough University. I spent 5 years there at the end of the 90s as a research fellow. I'll be talking about exemplar-based deep learning. And first of all, it's a different style of talks. I have seen the talks today and they were very impressive. Some of them, many of them were about robotics, one about hardware implementation. Mine will be quite different. So it will be mostly about algorithms. But there is a close link because you will see that the application of what I'll be talking about can go not only to robotics, to autonomous systems more generally, and also algorithms and hardware implementation go hand by hand, as we already commented earlier. I'm, as it was mentioned, leading a center which is called LIRA, Intelligent Robotic and Autonomous Systems, which is very close to all the talks and close to the possible application areas. So I'll move on because of the shortness of time. I'll start with first the problem, the context and challenges, and then I'll briefly sketch the approach, and then I'll move to some applications, but this will be mostly some images, just one video, no sound, so not so attractive as the previous ones, but interesting as well, nevertheless. So what is the problem? So everyone actually nowadays is aware about this environment in which we live, where this new type of achievements, which are very often related to deep learning, machine learning, AI, let's say, started to be popular not just between scientists like us, but also between wider audience, including even politicians and so on. Part of it is, of course, the buzz and the way it was taken and the opportunities this offers. But there is actually a much longer story in this. If you look at the problem itself, deep learning is nothing else but a different form of artificial neural networks, which started more than half a century ago, if you want. And there was a peak when I was doing my PhD in 90s, even late 80s. And of course, there was later the winter, so-called, for the neural networks, but there is a resurrection. There was also research on neurocognitron and other computer vision research achievements, which were actually linked together But a big contribution to this was also the huge growth in the capacity of the actually hardware or the computing devices, which were not only miniaturized, but also they become so much more powerful that it was possible to implement artificial neural networks with more than 1 billion neurons in them. Of course, this grabbed the publicity, and there are a lot of initiatives. I'm part of several of them, like this Alice, Claire, and a number of projects that they run. And people started to be really slightly hungover, like, okay, we can do everything with this. Everything is achievable, just give us the data. But if we think more realistically, this success was mostly in games, which means well-structured problems. So if you look at the real-life problems, there are many more challenges which are different from achieving success in chess or Go. And one of the contributing factors, as I mentioned, for this reality is the growth in the power of the devices, hardware, and so on. But also another, which is probably less popular, but is visible nevertheless, is the growth of the data. It's not just the amount of data, but also their character, their nature. They are heterogeneous data nowadays, not just tabular type of data, temperatures, pressures, and engineering type of data, but more and more images, which was not the case in 80s and 90s, because images started to be digitalized around 90s, 80s, 90s. Widely, but more and more even text as well, natural language processing, and other type of data. So we have a heterogeneous type of data growing exponentially, reaching huge amount, which is astronomical now, zettabytes or whatever, even per day, terabytes. Each one of us holds huge amount of data literally in our pockets. These are the USB flash sticks, mobile phones, smartphones, and so on. They have in themselves a lot of data. And this led to a reality where there was a temptation to shortcut from the huge amount of data, like what is called end-to-end process, to the solutions, but without going into the deeper understanding or uncovering or getting forward to the advancing the causality or the cause effect or the reasoning as well. So this actually led to some negative as well aspects, like dangerous fatal accidents. Sorry about my voice. Fatal accidents, like with the driverless car reported in 2018. Some other misuses of this technology, if you want, and a widely recorded case with Compass, which also border ethics and other principles of science. And this was a matter of concern for a number of governmental institutions. For example, in UK, House of Lords had a selected committee to which I was reporting as well. And in other countries as well, they started to look much more closely in terms of regulation, in terms of constraints. EU has not only GDPR, but currently is still not accepted, but a wide, in advanced form of development, AI regulation. AI Act is called, and also US is considering as well similar. And in terms of science, paper was published by Cynthia Rudin, which was directly called "Stop Explaining Black Box Models and Use Interpretable Models Directly Instead." So what is the problem? The problem is that there are two sides of the coin. On one hand, these billions of neurons or dozens of layers of neurons can give us the accuracy and precision, which is good, but they also have a lot of problems. They bring a lot of problems. Not only they are data hungry, so we need huge amount of data, require a lot of training energy, which was mentioned in the previous talks, energy and compute power and specific type of hardware like GPUs and so on, but also interpretability and trust are related, and it's not transparent anymore. Human cannot verify or check the decision in the same way as they can for simpler models. Why this is important? Because even if in rare cases, it's possible to get a wrong decision. I'm sorry, the slides are actually running automatically quickly, and I'll be returning them. I'm sorry about this effect. So in very rare cases, wrong decisions can be made with high confidence. This is an example from a paper, but there was another real life accident when the moonlight was mistaken by a Tesla car for the yellow from the traffic light. So in rare cases, not very often, but in rare cases, such well-trained models can give misleading conclusions or classifications or recommendations, and moreover, with high confidence. They are not saying, okay, maybe. They are saying, yes, definitely this is a guitar or penguin or traffic light, when actually it is not. So then it's important to get into the model and to understand it better. So the alternative, which I will be talking about, is exemplar-based or similar to prototype-based models, which can give you same levels of accuracy, but much higher explainability. And this is a form of deep learning, which is not the traditional one. So it does not require tedious error bug propagation training and so on, which also has implications about parallelization, about hardware implementation, and also even in collaborative federated learning forms, you can exchange meaningful prototypes or exemplars rather than billions of abstract weights that have no resemblance or they bear no direct link with the physicality of the problem that they model. So I'll be talking about alternative type of deep learning, something that Professor Chilu mentioned, and if it comes, so this is an alternative type of deep learning. It's talk about algorithms, and towards the end, I'll show some examples of its implementation. But first, the challenges. So the challenges are to bypass this temptation to shortcut causality. Parametric or prototype-based or exemplar-based models, they're an alternative. I'll be talking about this. Also to look at functional or symbolic linguistic. So symbolic and linguistic representation has been around for a lot of time, but these dramatic results in terms of accuracy put this aside. But is it possible to bring them together and to have both sides at the same time? So this is the question or challenge. Machine learning with reasoning together rather than one or the other. Also, local or global model. Do we need to try to find a global model in terms of inductive learning, or we can use transductive learning and locally based generalization rather than global generalization? Also, active learning, extract model structure in a different layered way. And the data very often nowadays are streaming, not only heterogeneous by nature, but also they are not static, they are streaming. You have video, you have speech, you have many other forms of streaming data, and they require a completely different type of model, a recursive, non-iterative, and so on. Why? Because you cannot model all the variety of objects, all of the variety of signals. You can model if it's a sinusoidal or repetitive or periodic signal, yes, but if it's non-stationary, and many of the signals are, like for example, stock exchange or like economic data, or even some human behavior data and so on, they are not necessarily periodic or repetitive. It's hard to model them, all the variety of these models. There are, let's say, development of a disease or progression, so you cannot model all the possibilities in advance. Streaming data have this requirement for, they have this evolving nature, so they have exploratory, more like in robotics, open space. So these are all challenges and low memory computational costs, which I mentioned as well. So how to address this? I'll briefly try to explain the next 10-15 minutes, probably 15 minutes, the essence of the approach, which I try to summarize in a book, my third research monograph, which is shown here, which is called Empirical Approach to Machine Learning. So in the nutshell, or in the core of it, there are 4 quantities which are entirely data-driven. So the essence is that entirely from the data, without any human intervention or predefined different thresholds or other interventions, we can extract information about the data pattern. It's a little bit strange because in the literature on deep learning, machine learning, you can find very often criticism of the previous approaches, which are not of the same group. And they say handcrafting. Instead of handcrafting, extracting features, we'll do this end to end. But in fact, there is a lot of handcrafting in the deep learning approach itself in the neural networks. You need to determine how many layers, which type of activation functions, ReLU or another. You need to determine different parameters like stride or kernel size and so on and so on. In the approach that I'll present in the next 15 minutes and which is described in much more detail in, let's say, about a dozen of journal papers, including in PAMI, in IEEE transactional cybernetics and fuzzy systems and so on. You can find this organized well in this book, which is 400 or 500 pages. I'll try just to summarize the essence. Everything is combined and let's say the core comes to these 4 quantities, which are very simple: cumulative proximity, standardized eccentricity, data density, and typicality. And typicality is actually nothing else than conditional probability, and data density you probably know. So actually they're not completely unknown quantities. Cumulative proximity first. So if we have data, even if they are very complex, we can always plot them or represent them in the data space or feature space. I think this is something that everyone knows in pattern recognition. Of course, in reality, you have not just 2, but many dimensions, but there are many different methods to show this. It's a simplistic example. You can use TSNE or another method to show many more dimensions together. But let's assume we have just 2 dimensions for simplicity, and we have a lot of observations, usually millions, billions, thousands. In this case, just a handful, about a dozen, just to illustrate the idea. So each measurement, each item that you have to model can be represented as a point, as a dot. It's a vector, in fact, 2-dimensional in this case. The 2 quantities, the first quantity that we introduce is cumulative proximity. It's nothing else than the sum of square distances between each pair of points. So the sum square distances, and we don't specify even the type of distances. It can be any type. Of course, Euclidean, very commonly used, Mahalanobis, but can be cosine, can be Hamming, Hanning, and all sorts of different distances. It works for all of them. We can also calculate easily the mean distance, of course, which is also trivial. So I think it's quite trivial so far. The next step is we can find the inverse of this mean. We can find it's reacting slowly. You can find the inverse of this mean cumulative proximity, which we just introduced, pi with the hat, or sorry, pi with the bar. This is the mean proximity. So inverse of it is 1 over pi, or you can normalize, let's say, the cumulative proximity pi with the mean pi. So this is like a normalized cumulative proximity. And there is a multiplier 2. It's not by chance, not by coincidence, simply because the distance from point A to B is the same as B to A, and we need this multiplier to take this into account. So essentially, this is a normalized cumulative proximity, but it has its own properties, and it's a separate quantifier, if you want. Eccentricity. It's called standardized because it's a normalized quantity itself. So this value, eccentricity, can range its like positive value, as you can see, because it's a sum of distances, sum square distances. So it's always positive. But if it is bigger than 10, in fact, it's exactly the same as 3 sigma rule. So essentially this Chebyshev inequality, or otherwise, if we have a value bigger than 10 of the standardized eccentricity, we have some strange points which are rare. If we go back, points which are close to each other, they will have low value of eccentricity because they will have high value of, low value of the cumulative proximity because distances will be relatively small. Points which are far away, like point A, which is not too much far away, but it can be even further, will have longer sum distances, like these blue lines here, and they will have higher value of eccentricity. If this value exceeds 10, because it's normalized, it's just 10. It's not related to the actual value of the features. then we have an anomaly. So it's actually translates the very widely used and popular Chebyshev inequality test for anomaly detection. And anomaly detection is very important thing to something very simple, just to check if eccentricity is bigger than 10. But eccentricity has even bigger role, or is much more interesting actually than that. You can, I have a paper where you can find anomaly and in real time based on eccentricity, but its main role comes from its own inverse. Its inverse is actually what we call data density. So data density is the inverse of this eccentricity, which if you go back, you'll see it's normalized cumulative proximity divided by the cumulative proximity and the coefficient 2. But otherwise, it's the inverse of eccentricity. So this type of data density, and it can be shown that this, if you go further from cumulative proximity to the actual distances, it can be demonstrated that if you use now Euclidean distance, you'll get this expression that I'm showing here. If you use Mahalanobis, you'll get almost the same, very similar, with the only addition that between mu, these two mu's here transposed and the normal mean, you have an inverse of covariance metrics as well. So practically the same character of the function, which is nothing else but the Cauchy function. Why? Because we have 1 divided by 1 plus something square. So this is a Cauchy function expression, or kernel if you want, which represents data density. It has very interesting properties. It's like membership functions in terminology of fuzzy sets, and it resembles a distribution of probability, but it's still not a distribution of probability. But more important, it can be recursively updated. You can recursively update very easily the mean. It's trivial, you know it from school, but you can also recursively update this inner product as well. And then you can update the whole this quantity. In fact, this is something that I called recursive density estimation, and I published and even patented. There is still a holding patent, granted US patent on this. Why it is very important? Because you get just one number, which is scalar. It's just one digit. Even if you have not two, but like in deep learning, 4096 or 1000 features, still the value of D will be just single value between 0 and 1, guaranteed by design, because it's between a Cauchy function. So it will represent as percentage, if you want, like 82% or 0.82 will mean it's representing very small variance, because in fact this is variance. So you can compare one image with as many images as you want in the past, and you can get the value, single value, which tells you how similar a particular image is to as many images as you want. So this is very useful already, the density. But we go further. We look at the normalized value of density, which is the typicality. But first, as I mentioned, recursive density estimation is essentially a recursive version of the very well-known kernel density estimation, which is Parson Windows. And it's not by coincidence again, because you can look at this as a kernel, Cauchy kernel, and also Cauchy is nothing else but approximation in first order Taylor series of Gaussian. And RD itself, recursive density estimation, I mentioned patent and so on, can be applied to many interesting applications. I have papers on this and projects. This was the STL project. You can detect very quickly anomalies. For example, in this application, phone calls based on the metadata, not of the conversations, not NLP, natural language processing, but just taking into account the time of call, who calls whom, and so on, distance between the callers, and so on, and maybe age. So 12, I think, features, which are very simple to process. For microseconds, you can determine out of hundreds or thousands of calls, strange calls. For example, call because it was New Zealand in the strange time of day, maybe very long call, or so on. So you can, it depends how you define the anomaly, which features you are looking for. You can find the strange call for that person or strange call overall, and so on. You can also use it for SLAM. SLAM was mentioned here. We have papers on self-localization mapping based on visual input of image directly and processed in real time. So the robot travels around an area that never has been, and it calculates this value D that is shown here, data density, and you can see how it fluctuates. And the drop of D means something quite different. If you have the same environment, let's say green, blue sky, whatever, the images are different, but they are very similar. So you have fluctuations, but not huge drop. When you go in the underpass, which is yellow and so on, quite different, then you have sudden drop and so on. So you can find all of these throws, or let's say minimum points, local minima, and you can call them like landmark 1, 2, 3, and so on. And you can automatically build a map even of geolocation where they are in your travel, and you can pass to another, if you have a swarm of robots, information. So you actually are building a map fully unsupervised, without any supervision, based on full image, not just on single pixels, so in real time, without any human involvement. And several robots can communicate and can self-localize and find themselves in this environment. So this is quite interesting on its own already, density, but we move further. So the final fourth quantity is called typicality. As I mentioned, in fact, it's the conditional probability or probability, but let's first define it. It's very simple. So I already defined the density, which here is D with index N, because it's discrete, because there can be a continuous version as well. I'll talk about this later, but this can be seen as a weighted sum. So we have a weighted sum of this density, where the weights are nothing else but the frequency. How often do we have a measurement, exact the same measurement? And in fact, we combine two completely different definitions of probability. If you paid attention when the probability theory is introduced, there are two quite different formulations which are actually introduced one after the other, almost without any detailed comment in all the books, if you take Bishop or some textbook or whatever. One of them is what is used in schools, which is just F divided by sum of F, which is trivial. It's just the frequency. So you throw the coin or something else, and you count the number of occurrence of one fact divided by the totality of all facts. This is the discrete definition of probability, which is used in schools, but this is not what practically is so useful. Much more useful in practice is the distribution, which is like Gaussian or other distributions, which is actually the discrete version of it is this D, data density. In this case, it's a Cauchy distribution. So when you combine the two together, you get something very interesting, which we call typicality. You get the picture on the right based on real data from climate near Manchester, England. You can see the wind chill, temperature, wind gust. In fact, there were 5 different features. We show only 2 of them. But what is interesting, you can see already the local peaks and the character of this. There are 2 seasons very clearly seen here. In fact, we take mostly the data from the winter and summer, but in UK, in fact, there are 2 seasons. I mean, mostly, not so much 4 seasons. You don't have clear summer, you don't have clear winter. And in fact, this looks very similar, resembling, with the bins, the histogram. So in fact, it can be seen as a histogram with size 0. In any histogram, the key issue is just single parameter, bin size, but it's a big issue, actually, a big problem, because we need to predefine how big is this bin. For example, 1 degree centigrade, or maybe 5 or 10, and the same for the, okay, even if we normalize, so they are not different physical variables, it's still a problem. Why? Because if we take it too small, we'll need huge amount of this. If we take it too big, we'll lose information about the character of the curve. But not only this, if we take even 2 dimensions, as we have here, you already have at least 10 values for 1 by 10 by 10, and you need 10 for the value of the histogram, so it's already 1,000. But you have 5 values, as I said, so you have 10 on power of 5, and in some real problems you have hundreds of them. So you need huge amount of actual data in order to get this character of the distribution. This is one reason nobody is using histograms too often. Well, here you get the histogram automatically, and the pattern is the same, and you just don't need too many data. You can start with 2-3 points. Of course, with single point, it will be hard because you need the distance. in order to calculate the density, even in the form that we introduced it. But still, you need just 3 points. So like here, you immediately start to get the distance with 2 or 3 points. 2 points is also a bit trivial because you get just the distance between A and B and A. But with 3 points already, it starts to be interesting. So you need very, very small amount, few shot learning, as they say. And not only this, but if you look deeper, in fact, typicality, if you make a continuous envelope around this curve here, you get nothing else but exactly the probability distribution. And this is also the main property of probability is satisfied, that the integral is exactly 1, guaranteed, and the values are between 0 and 1, and the maximum is much less than 1. Because if you look at the density itself, the maximum is exactly 1. Well, here it's much less than 1 because the total integral is 1. So we essentially predefined the conditional probability through the experimental data, and without assumption of the type of the probability distribution. So we didn't assume how many peaks or local modes it will have, because usually in reality, people assume, let's describe this with a Gaussian or Cauchy even, like we did, but single Gaussian or Cauchy. In fact, we get the mixture, and we didn't predefine how many there will be. It comes from the data. We monitor the data, and if we have more data, there will be more of these peaks. So the data cluster themselves, and they organize themselves, and they form these peaks. So if you compare a single Gaussian assumption, will be the green light. If you take mixture of 2 Gaussians, if for some reason you know that there are 2 seasons or whatever, you get the black line. And what we get without any assumption, starting with 3 data in real time recursively, is the red bars. And if you spend a lot of time, efforts to get the histogram, you'll get the blue bars. So all of this is just some theory, and you'll say, okay, why we are listening this? I mean, I'll come to the practicality. So essentially, we can get experimentally, or as I say, empirically, the distribution of the data and the probability distribution, and you can look at the peaks, local modes, which are the most interesting points. These are representing some prototypes. And we can look for the actual data nearby, and this will be the exemplars. Otherwise, we take a specific car to be an exemplar or example of some thing that we want to describe. Or some patient, we have the patient John Smith, who will be representative of some type of illness, and some other patient to be representative of something else. And this also has another dimension, which I have another paper, anthropomorphic, I call it machine learning. It's not neuromorphic, but anthropomorphic. It's very much like humans learn, because as humans, we learn exactly the same way. We compare what we see as new with the examples of what we have seen before. We don't build complex mathematical models, polynomial or whatever. So one assumption is that in our brain, there is a network and we build this model. I'm not quite sure. Maybe there is a link between this and the reasoning, but at a different level of the mind, there is also the reasoning. So the way we understand it is not through these thousands of neurons. The way we understand it is through the examples. You say very often, oh, I have seen a car like this, or I have seen a fruit like this, or whatever. And these are the exemplars, peaks of the local distribution of the data. So they are not random, they are result of clustering of this quantitative process that I just tried to describe. So there are 2 videos which I hope you can see actually as a video. I'm playing them on my computer, which demonstrate that in the data space, if you have more and more data, you can build this essentially distribution. So it's evolving, dynamic in time. It's not something static, one-off. And then you can build even semantics. So you can build rules to describe them. If this looks like this prototype, then it's cold day or winter day or whatever. So you can put any labels, human understandable, as you like, but the core of this mathematics of this is derived in a sound way through the exemplars, through the examples. But you can go several levels, and this is where deep learning comes. If you do it just once, you get a lot of local prototypes. Like in the climate, you have a lot of exemplars. It's not just 2 seasons. 2 seasons is the higher level of aggregation that we actually usually apply. We say, okay, cold and hot, but there are many hotter winter days and colder summer days and windier and so on and so on. So you have a lot of detail before you come to these just 2 seasons. And you can build a stack of different levels of aggregation. How do we do this practically? Very simply. So the first level, we just start with the real data. Oh, sorry, let me see where is the video again to play. So the first level is we start with all the real data. Then we apply our method once, and then we get a lot of local peaks, if you want. Then we forget about all the real data. We take only the peaks. We reduce the data 5-6 times. It depends how many actual data there are around these prototypes. We forget or ignore the other data. We take just these peaks, and then we apply again, and then we get much less, which are another level of aggregation. And then again, and at the end we get just 2 seasons, let's say. So we can use all of them. So we can have one level of prototypes, another level of prototypes, another level of prototypes, and so on. But before we start this, first we need to extract this mean and this inner product, if you remember, density, these 4 quantities that I mentioned, and the typicality or conditional probability. We do this unsupervised per class. So let's say we provide a lot of examples of images of cars, and we extract features, then we calculate these quantities, then we get one set of prototypes, probably too many, then we reduce them, reduce, and then we end up with few prototypes of cars. Then we have 4 houses. And for cars, there may be some sports car or smaller and so on. There will be different prototypes. And at the previous level, we can have many more of the same sports cars and even more and more. But still, these are much less than the actual data. And then we do a local decision per class, the winner per class, and then we take the global decision, and then we take the final decision. Features can be anything. If it's image, it can be GIST, histogram of gradients, but we can use even a pre-trained deep network just to extract the features, not to actually apply the reasoning or understanding. And what we achieve is not only a computationally much more efficient network, because there is no need for error back propagation, so on, everything's recursive, but also it's accurate as the others, or even more accurate. And also it's explainable, because you can assign rules which are linguistic, and they say, if it looks like this, it's car, and so on. So this is description of the network. I'll skip it. I'll show now some examples of how this works. We started to apply this to iRoads and Kitty and other publicly available data, but also this was part of our 3-year funded project by Ford Research and Innovation in Palo Alto, which we visited a few times just before COVID. So you take images from the front screen, for example, of the car, and you try to classify into type of, is it a sunny day, if is it a snowy day, and so on and so on. Of course, we apply first, we used in this case, as I said, pre-trained deep network to extract the features, then we calculate the density, typicality, prototypes, and mega clouds, which are like prototypes of a next level, if you want, of aggregation. And after it's pre-trained such network, when we provide a new image, which is snowy, we compare essentially with all the prototypes for each of the classes that we have here. Only 2 are shown, but you can see the dotted line, so there are many more. And then you can find the winner per class, and then the total winner, the overall winner. And this is how we determine the label. So you gain explainability and of these exemplars, because these are exactly examples of sunny day. These are examples of snowy day. And then you can calculate the similarity level. So everything is clear. There is nothing abstract or difficult to understand by a human. Further, we try to find the local optimality, or otherwise we pose the question, okay, are our prototypes positioned in the data space in an optimal way? So they can be optimized with Karush-Tucker conditions locally, and we achieve better result. But here there is a small payoff, because this is not recursive anymore. There are iterations, but there are not too many, because we start with a very good initial position. So it's just small kind of shift movements around. It's very local. Then we move to another image processing problem, which is also very popular. This is MNIST, optical digit recognition. Very simple problem, actually. And we compare with the best results, which already have been 99.5% accurate. So it was difficult to beat them, actually. But all of them, we noticed the best by Jürgen Schmidhuber's group and so on, they were using one thing which is called elastic distortion, which is very kind of questionable because it's hard to repeat, because they say random changes are made and you cannot repeat exactly the same. You can only repeat on average. So we decided not to apply even elastic distortion at all. We applied the other pre-processing techniques like rotation, scaling of images, segmentation. We applied the same techniques as everybody else. We used GIST and HOG descriptors, and we extracted rules which are very meaningful. Not only we got the high result, which I'll show later, but we extracted rules which look like this. If the image looks like this, or like this, or like this, and so on. So these are 6 prototypes or exemplars here. In fact, we had more per digit. Out of the 6,000 training digits provided, we extracted a few hundred for each of the digits, which are exactly examples how different people write this number. Then the class is 0, and so on and so on. So now to the results, or how exactly we get the results, and then actual results. So once we get an image like this 4, we compare with all the prototypes from all the digits. So we don't know yet which is this digit, and we take the winner per class. So the winner for 3 is this, the first one. The winner for digit 2 is this one, and so on. So the overall winner was for digit 4, and it was clearly better than the others, but the second best was 9. And it's not coincidence. If you look as a human, even if it's not 4, the next closest resembling digit is 9. So it makes sense. And this digit is 7. And the next most similar is 4, because they wrote 7, as you can see, in some countries they write like this, but it looks a little bit like 4 as well. So it makes quite a lot of sense. And this is how we do the validation. It's similar to what I shown earlier, but let's look at the results. So what we achieved is 99.55% accuracy without using any GPUs, with a normal laptop for 2 minutes, and without using this elastic distortion, which means that we can repeat our result as many times as we wish. We will get exactly the same result. While the best published for the same problem was, I mentioned Jürgen Schmidhuber's group, both results are from his group, 99.77, which is already hard to beat. It's only 23 examples wrong out of 10,000. And you can see actually the results that are wrong. Some of them are actually very difficult even by a human to determine. This second one and this one probably. But they used 35 different deep neural networks, and they trained 14 hours them using 2 GPUs. And they use this elastic distortion to change randomly the inputs, which may by chance exactly coincide with these strange outputs. And there was no even way to exactly reproduce exactly what they used. So it's a little bit questionable, but in any case, we achieved very high results and fully interpretable with these rules that people can actually understand. So then we move to more interesting and more challenging problems. We move to Oxford Research Lab problem, which resembles what you experience now when you cross borders. So these are images, faces from 40 different people, 10 images from each person, so 400 images. The task is to take 1 from each person, 40 images, or 2 or 3 or 4 or 5 from each person, up to, let's say, half of the data to train any model, so that you can recognize the remaining 9 or 8 or 5 images. We did this, and we compared our results with other deep neural networks, and we surpassed all the published results, and we got even 100% with 5 images for the remaining 5, all of them correct. We got 90% with single image. But more interestingly, we extracted rules which are very meaningful. In this case, we didn't use the full image in our rule. We used only segments. We split the image into tiles or segments, and we use these segments. And the rule looks like this. If the segment on the top right looks like this, which describes the hair, and the next segment looks like this, which is the eyebrow and the eye and so on, looks like this, then it's subject 1. or if there is a beard, if there is mustache, and so on, it's subject 11, and so on. So it's very much human-like, anthropomorphic, or similar to what humans will do. So we use these exemplars or examples or prototypes. So we combine this with very high accuracy and very quick and computationally light way of training. We moved then to remote sensing, Singapore data, and we achieved also very high results. In fact, this is not the highest that we get, 94%. We get 97 with another setting of the same problem. And again, we extract the rules as well. Then we moved and we challenged ourselves and we said, can we beat some world records? So in fact, we beat 3 world records. The first one was for Caltech 256, relatively famous problem. You can find it on Kaggle and so on. The best published result before we applied this was 74.2%. We get 75.41%. It's very hard problem because there are 257 different classes and there are images, small images of different objects. So 257 different type of images. And we publish this. Not only this, but we extracted rules. If it looks like this or like this, and you see it's rotated, it's not the same type of machine and so on, then it's bulldozer. If it looks like this, mountain bike and so on. Then we move to Caltech 101, which is simpler and therefore the results are much better. We had another improved version, which we call DMR or deep machine reasoning, and we got 94.31%, and also to faces data. So then we put ourselves another issue to, is it the time? Or yeah, another issue to challenge ourselves. What can we do with unseen classes or scenes? Imagine you train the car to recognize 5 different things like urban environment, rural environment, snow, summer, whatever, but suddenly it is in another situation that it doesn't know anything about. It's not something that you trained it for. Usually in classification, you will notice that problems are set up very kind of strictly, like there are 2 classes or n classes, 3 or 5 classes. You train data on part of them and you test, validate on remaining data, but the number of classes is exactly the same. You never have a problem where you train to recognize between pears and fish, and then you provide car, and let's see what the classifier will say. You never provide new class that has never been used. We try to challenge this and to say, okay, let's see what happens. So we developed an approach first to recognize if this is the case, if the confidence in our recognition is very low, we say it's a new class. We don't know about this anything. And in driverless cars or in cars in general, this is very often. The same also in cybersecurity, you have new attacks and so on. But in driving conditions, you may come into a situation that you never expected. And not only this, but because images are taken 25 per second, for 1-2 minutes, if you are in a tunnel, you never trained on tunnel, or there is a light in the tunnel or something like this, you have actually very quickly hundreds or 200 or maybe a few thousand of images of this new type, all of them. This is very convenient to train for something new without any supervision. And you can recognize snowy scene, night scene, but what will happen if suddenly you provide something which is rainy day, and the deep network which was pre-trained was saying with a very high confidence this is night, but actually it was rainy day. And we calculated the density, which I already described, and when there is a density, actually this is the winner class. When we decide that this is the winning class, there is the value of density attached to it, or similarity. And when this value drops, this is essentially the confidence. So the confidence drops suddenly. Why? Because it's a new environment. And actually there are many of these examples because of the fact that I described. You encounter not single new image, which may be noise, maybe something else, or like in cybersecurity attack, but in driving, very often you encounter hundreds of new types. And this can be very easily seen here with the drop of confidence. And when we notice this, we start to learn without any human involvement, and we say, oh, this is new class 1, and the next is also new class 1, and we start to recognize it with very high accuracy without anybody training this classifier to recognize this hail, for example, which looks like snow, but is not the same as snow. You know, hail looks like snow, but is more like rain. And we recognize it with 99% accuracy, actually. So then we move to COVID, which is another very challenging problem. And we got real data, and we looked at the CT scans, and we applied the same approach. And again, I'll try very quickly to go through it. We got very high results, but also we were able to extract these rules, and the accuracy was really very high. And we are currently working on this to take it further in a project. And we also extract rules. We extract rules which are telling us if it looks like this or so on. So these are the examples. Then it's COVID, otherwise it's non-COVID. And further, we moved into segments, not the full chest CT scan, but only segments, because malicious areas are actually part of it. And we did the same. And then we were able to extract, build a model with examples of COVID affected and normal patches of the COVID. This also allowed us to estimate the percentage of how much the lungs are damaged. And this will help radiologists. Like here, you can see this is the damaged area of the lungs. And this can be used to not only make the conclusion, is it COVID or not, but also to evaluate the percentage of affected area of the lungs, and also give some explanation. So it's explainable form of deep learning, if you want. And the accuracy is very high. And this is actually published in an archive, but currently pending a journal publication. So one video, as I said, I also have some videos. We were able to, in real time, recognize, classify pedestrians, cars in a real busy urban environment using the same approach. This is from the NewSense database. And then we move to aerial photographs for flood detection with the European Space Agency. This is a currently ongoing project. I'll just mention briefly. I'll skip the details. I'll show you some results. So applying the same approach, we try to distinguish between floods and when there is simple just exceed level of water, but no flood. And we train this, and we also use the same approach with segmentation, and we separate between water and land, and whether these water areas are exceeding what we expect, and then there will be announced flood. So we are working on different applications as well. This is one of them. And not only accuracy, as I said, calculation simplicity, but also explainability is important. So currently our best results for so-called world flood dataset, which is taken by Copernicus program, or actually another one, Intelsat 2, I think. We get around 87% correct accuracy, but also you get this explainability as well. Here we have even actually higher, 0.9. So in summary, I tried to present very quickly and very briefly a powerful approach which is alternative to the conventional or mainstream deep learning. So the talk was mostly about algorithms. It's centered based around exemplars or examples or prototypes, rather than around highly parametric models with very complicated structure. Therefore, the learning is much easier because you just need to cluster the data, find the local peaks or maxima or means essentially, and it's much faster and easier. It allows symbolic representation, which is much easier for humans to understand. If it is like this or like this, then you get this result. It allows it combines the layered architecture from deep learning. It can be represented as a network because there were much simpler examples of artificial neural networks, which can be represented this way or that way, like radial basis function neural networks and so on. This is much more complicated, but it's also of this type. And it's fully verifiable, analyzable, repeatable. It helps in defense for assurance, what they call assured AI or trustworthy AI. It's non-iterative, non-parametric, allows high levels of parallelization because each prototype can go on a different device or can be trained on different machine or group of prototypes. And it achieves very high levels of accuracy comparable to human level or better. I mentioned number of publications. I will send the slides to the organizer so you can check this. 2 books, the one that I talked about and another one, 2012, Autonomous Learning Systems, are very relevant. Also, all our software, not all, but some of our software is on GitHub in Python, so you are welcome to visit this and to inspect. Thank you very much for the opportunity, and I'm open for questions.